Hello, everybody. So today we're going to be talking about some limit theorems in probability theory and some applications. So we'll first talk about different notions of what it means for a series to converge in the sense of probability spaces, and then we'll talk about two major applications of these notions of convergence, which are the strong and weak law of large numbers, as well as the central limit theorem. So we'll start by quickly reviewing the notion of a probability space. So the point is that we have some set and particular collection of subsets of sets, as well as a probability measure, which maps a particular subset to a number in the interval here. And the key point is that if we have disjoint sets AI, then the probability of the union of these AIs is equal to the sum of the probabilities of each of the individual subsets. Right. So if in addition to this, we have the data of what's called a measurable function mu, in the probability lingo, this is what's called a random variable, then we get a particular distribution by essentially pulling back the set under the random variable and then taking its probability, right? And the implication is that this is just going to give us a typical function on Rn in the sense that we can manipulate from familiar concepts in essentially calculus. Right. So we're going to be dealing with sequences of these random variables, these measurable functions from earlier, and we have a variety of different notions we can talk about for convergence of such a sequence. So one sense is just convergence in the sense of distribution. So this means that each of these random variables has an associated distribution, as we talked about earlier. This is just saying that the distributions themselves basically converge in the typical sense. So in terms of this limit. This is not quite the same as convergence of the probability density functions. Uh, this is more closely related to convergence of the cumulative distribution functions. So this is a relatively weak notion of convergence in the sense of probability theory. A stronger notion is what's called convergence in probability. So in the more general sense, this is what's called convergence in measure. And this is basically saying that as we get for essentially as we go to higher and higher n, the probability of kind of a strange event, which differs from the limit, becomes essentially vanishingly small. And in the limit is precisely zero. So that's what's encapsulated by this notion. As I said, heuristically, essentially, the probability of unusual outcomes becomes less likely. So this is true for any choice of epsilon. And note that the limit is outside of the probability measure here. So in particular, this is stronger than convergence in the sense of distribution. And then the strongest notion of convergence, which we'll be talking about, is what's called almost sure convergence. And this is almost everywhere in more general measure theory lingo. This is saying that if we actually take the limit here uh, over all of the points, the probability of that is equal to 1. So it agrees essentially everywhere, which is why the name is appropriate. And this is the strongest form of convergence we'll be dealing with. Okay, so in terms of these applications of these notions of convergence, we'll talk about the concept of independent and identically distributed random variables. So we're going to have some collection of these. They're independent in the sense of probability theory, and identically distributed means that their distribution function is going to be the same, right? So in particular, each one of these is going to have a particular mean and variance, regardless as to which random variable in the set we're dealing with. Okay, so as a first application of our convergence here, we'll talk about the weak law of large numbers. So the convergence that we'll be dealing with is in probability. So we assume that we have a sequence of independent and identically distributed random variables, and the expectation will be mu. This is going to be the same for each of these. They're identically distributed. Then what this is saying is that the probability of this particular combination, which is written out here for a given n, uh, tends to 0 as n goes to infinity in probability. So what this is the sample mean, basically, for the first part, and then we're subtracting out the mean associated with each of the distributions. Okay. And then we can improve upon this by actually showing that this is true at the level of almost sure convergence, and this is what the strong law of large numbers is. All right, so this is just rewriting out the definition from before. So what's the significance of these laws of large numbers? Right. The point is that what this is saying, regardless as to which mode of convergence you're using, is that given many trials, that's what the sample mean is expressing, we expect the sample mean to be very close to the mean, right? So this gets increasingly true as we have more and more trials. That's the statement of each of these theorems, and this is the principle behind how casinos earn money, right? Because there's a lot of people in there, a lot of different trials, expect to be getting the average return. This is also the justification for Monte Carlo methods with regards to simulation as well. Okay, so another major application of these notions of convergence and probability spaces is the central limit theorem. So again, we're going to have a collection of independent and identically distributed random variables. Here, we're also going to specify the variance. So these have an expected value of mu, and then a variance of sigma squared. And then this particular combination, uh, as n goes to infinity, is increasingly represented for any given a in terms of the following cumulative distribution function, which is associated with a normal random variable, right? Standard normal. And this convergence is in distribution. So this was the first notion of convergence that we were talking about, and that's what this means. Okay. So the significance of this is that from the law of large numbers, we know that the sample mean is going to approach mu. The question is essentially what the deviations about that look like as it is approaching the sample mean. And this is what the central limit theorem is doing. And it's characterizing these deviations essentially in terms of a normal distribution about the sample mean, which is why the variance is relevant as well. So that's a little bit of intuition for the law of large numbers as well as the central limit theorem. And I hope these different notions of convergence and probability theory uh, are helpful, and I think it's a very interesting aspect of the theory. Okay. Well, I'll be posting some more videos on probability theory and related notions, and I'll see you next time. Thanks.